So we will use to compute perturbations in this case, we will use a rather commonly used gauge choice. We will fix our coordinates in the so-called zeta gauge or uniform density gauge. Which is defined simply by using the scalar field as our clock. So I imagine here's the global picture of space-time, time and space, and we're foliating the space-time using surfaces of constant phi. So these surfaces, these space-like surface, they all have phi equals constant. In other words, the choice of gauge is such that the perturbations of phi are 0. Okay, we have 2 degrees of freedom for scalar diffeomorphisms. I've used 1 to fix the clock to be phi, and I can fix the second amount of freedom that I have to fix the form of the metric on each of these slices. So Hij will be the spatial metric on each of these slices, and we can use the remaining gauge freedom to set this spatial metric to be of the following form. So the scalar perturbation will be simply a conformal mode, which we call zeta. And then there will be tensor modes associated with gravitational waves, and these we can write as e to the gamma ij, where gamma is transverse and traceless. So gamma ii is 0, and di gamma ij is 0. Okay? And meanwhile, the other degrees of freedom of the metric, namely the lapse function and the shift vector, are fixed by the constraints of general relativity. Okay, so we've completely fixed the gauge with this particular gauge choice. Now, it's true that this completely fixes the gauge, but in the more precise sense as follows. It fixes the gauge completely if you consider diffeomorphisms that fall off at infinity. If they fall off sufficiently fast at spatial infinity, then you cannot do anything other than what I wrote down. But there is room for gauge transformations that don't fall off at infinity, and this is what we'll focus on. So let us indeed consider the residual symmetries of the zeta gauge story. So here I'm going to follow a treatment of a following paper: Hinterbichler, KHOURY, and myself from 2013. And so we're just gonna proceed. We're gonna consider possible diffeomorphisms, so small diffeomorphisms, call them xi mu of x and t, that preserve this gauge. And these we will identify as symmetries, and they will correspond to some constraints on our correlation functions or Ward identities at the end of the day. So first of all, we want to preserve the fact that phi is purely a function of time. We want to keep the fact that we don't want to change our foliation. Phi should remain the clock. And so as a result, clearly, the 0th component, we don't want to redefine time, so the 0th component must be 0 for this diff. So all we can do is to do spatial diffeomorphisms to change the coordinates along the slices. And so we're left with xi. So this is all that we have at our disposal, xi of x and t. And so the goal is the following. If we manage to find field variations, so specifically we want to find field variations delta zeta and delta gamma ij, if we can identify such field variations in such a way that these guys mimic a diffeomorphism, then this will be manifestly a symmetry of the theory. So in other words, what we want to do is we want to identify some field variation of this spatial metric, which we wrote down. We want this guy to be a lead derivative with respect to xi of the metric. And I'll write down what the Lie derivative is in case you've forgotten. So where the Lie derivative of an arbitrary tensor Gij is given by Ck dk Gij plus di Ck Gij plus dj Ck Gi. Sorry, this is supposed to be K. Okay. So the idea is the following. A Lie derivative, of course, is just what a diffeomorphism would do. So if we can find field variations in such a way that delta zeta and delta gamma exactly mimic how a Lie derivative would act, then these will precisely correspond to, they will act exactly as a diff would. And since our action is assumed to be diffeomorphism invariant, this will be a symmetry of the action. So for every delta zeta and delta gamma that satisfy this property, we will have a symmetry of the theory. Now, this is actually non-trivial to solve, in particular because of gamma. Okay, so gamma being transverse and traceless, the equation is nonlinear in gamma. This is hard to solve, so we will do so perturbatively in gamma. So solve order by order in tensors. Okay, so in other words, what we want. So I want to expand everything in terms of tensors, so namely the diff itself, Ci, this diffeomorphism, will be a leading order diffeomorphism without tensors, plus a correction that's linear in the tensor, plus dot, dot, dot. And similarly, the variation of zeta itself, the field variation, the symmetry variation, also can be thought of as will be perturbed in this fashion. And finally, even delta gamma itself, it may have a piece, it will have a piece generically, which is zeroth order in gamma, plus etc. Okay? Now, for this discussion, we're not going to actually go beyond zeroth order, okay? But I'm just at least outlining what one should do. And in fact, in the paper, that's what we do. You can compute these corrections order by order. For our purposes, we're just going to stick to the zeroth order in gamma. So to zeroth order in gamma, let's expand both sides of this equation. So on the left-hand side, when I do the variation, so first of all, I'm working to zeroth order, but I have to be careful because delta gamma, when I'm going to take delta gamma, they can have a zeroth order piece. So I don't want to set gamma equals to 0 from the get-go. So we have the following. So let's do it. So by the chain rule, I can vary the zeta piece. So I will get twice delta zeta, e to the 2 zeta. And then here I'll have e to the 2 gamma, but now e to the gamma, but now I can set gamma to 0. So this will give me delta ij. That comes from varying with respect to zeta. Now I vary with respect to gamma, and then I set gamma to 0. So this will give me plus e to the 2 zeta delta gamma ij. Notice I've dropped the subscripts, the superscripts gamma 0, gamma 1, because it's all going to be implicitly to zeroth order in gamma henceforth. So that's the left-hand side. And the right-hand side, we just have to compute this Lie derivative. But the Lie derivative, this guy for sure, since I'm working at zeroth order in gamma, I can set gamma to 0 from the get-go. So here's what you find when you turn the crank. You find e to the 2 zeta. If you just compute this Lie derivative, it's really straightforward. You get twice ck dk zeta plus di cj plus dj ci. Okay, does that make sense so far? Yes? Okay, so the factors of e to the 2 zeta as they cancel across the board. And this is our final statement. So, and then we can isolate delta zeta and delta gamma. So we can do this as follows. Let's take the trace of this expression using the fact that delta gamma, being a tensor mode, has vanishing trace. So this guy is 0. So if we use this fact, I'm going to be left with 6 delta zeta from the trace of this guy. And then on the right-hand side, sorry, there should have been a delta ij here. There's a delta ij. This will give me also 6 ck dk zeta plus twice dk ck. Cancel the factors of 6. Makes it a third. And that's it. That's the variation of zeta. And then we can plug it back in to the equation and then solve for delta gamma. We can plug this in, and then we can solve straightforwardly for delta gamma. Here's the answer after substitution. We find that delta gamma will be equal to di cj plus dj ci minus 2/3, because I have 2. Sorry, but I divide by 2, so I'll have 1 minus a third. It comes about to be minus 2/3. Yeah, it's 2 minus 2/3, so it gives me at the end of the day minus 2/3 dk ck delta ij. Okay. Yeah. We're about to do that. That's right. We're about to do that right away. So far, it seems arbitrary, and now we will derive the one equation that it must obey. Okay, very good. Exactly. That's right. That's right. So I'm looking, in other words, precisely. So if I just did a random generic diff on this, I would start messing up with this form. Indeed, I would pick up some di dj of some scalar. So I don't want that. So I'm not going to consider the most general diff. I'm considering a subset of diffs which preserve this form. Meaning, if I can associate a field redefinition of zeta and gamma for those diffs, then by definition, I'm staying in the same gauge. So indeed, I'm not generating anything else in the spatial metric. All I'm doing is redefining the fields that were already present. That's right. But you're right. Also, it is true that I haven't said anything yet about Xi itself, but we're about to say something right now. Okay. Very good. So the one constraint we have not imposed is that delta gamma remains transverse. So in other words, the shift in gamma should be such that gamma remains a tensor mode. And so our remaining constraint is transversality. So we want to take the divergence of the delta gamma variation, and want to impose that this is 0. So that the divergence of the shift of gamma be 0, so that indeed it remains an honest-to-goodness tensor fluctuation. And this, you see, imposes the following. So if you take the divergence of this equation, you find Laplacian of Xi plus di, sorry, this should be j, excuse me. This is then di, so it's dj di ci, that's the second term, and then the last term minus 2/3, the same thing, dj di ci. Okay, so in other words, our diffeomorphism Xi is constrained to be satisfying the following equation, that the Laplacian, the spatial Laplacian on Xi plus 1/3 divergence, gradient of its divergence must be 0. Okay, so that answers your question. So any diff which obeys this equation does the job. Okay, so now we're going to study a little. Yeah, No, like anything else in perturbation theory, it's probably asymptotic convergence. In any case, for our purposes, we think the small parameter in this expansion will be the, if you want, the amplitude of tensor modes, which is very small. Okay, so that's our parameter. So to that extent, these are all small. These are all small corrections. But it's an asymptotic series like anything else. Okay, now I want to prove, for completeness, let us convince ourselves that indeed, if I impose that C vanishes at infinity, then I get no new solution. This will convince ourselves that for vanishing diffs at spatial infinity, our gauge was fixed completely. So indeed, let's suppose that Ci, our diff, does go to 0 at spatial infinity. And I want to convince you that, in fact, the only solution in that case is trivial. So let's see. Let's take the divergence of this equation. So if I hit this with a divergence, what I'll find Laplacian on the divergence plus, same thing, a third of Laplacian of the divergence is 0. Okay, so in other words, the Laplacian of the divergence is 0. And since now I'm assuming things fall off at infinity as usual, I can invert the Laplacian trivially. This implies that the divergence is 0. Yes? But when you plug it back to the equation, you're left with Laplacian of Xi being 0. So this implies Laplacian of Xi is 0. And again, I invert the Laplacian trivially, and therefore Xi is 0. Okay, so this confirms that indeed there's nothing new if I just focus on diffs that fall off at infinity. So non-trivial solutions, non-trivial diffs don't fall off. So first, let's consider, let's first consider the case where only zeta is transformed, to start with. So consider the case where, in other words, we want to focus on the scalar sector of these diffs. So we're going to impose that the tensor mode doesn't change whatsoever. So we're starting with gamma equals 0. We're not changing gamma, it remains 0. So the symmetries we're about to identify are symmetries of zeta itself, nothing else. So in this case, imposing that delta gamma is 0 to remain in the scalar sector gives me directly an equation for Xi, which is stronger than the one we derived by taking the divergence of the equation, clearly, because I'm not taking divergence. So we get a straight equation for Xi, which is the following. di Xij plus dj Xi is equal to 2/3 dk Ck delta ij. And of course, by taking the divergence of this, I'll reproduce this guy. But now it's a stronger statement. So who recognizes this equation? It's a well-known equation. Excuse me? It's a conformal killing vector on R3. That's right. So this is the conformal killing equation. On Euclidean space, on Euclidean 3 space. And this makes sense intuitively that this is the answer we found, because after all, if I'm setting the tensors to 0, our spatial metric is just this guy. So the only diffs that are left over that will keep me in this gauge will be conformal transformations on R3. Conformal transformations on R3 will pick out a conformal factor, which I can absorb just by shifting zeta appropriately. That's exactly what's going on. Okay, so that's obvious a posteriori. And so the solutions are dilation. Well, of course, of course there's a 10 parameter group. We have, let's just say that to start with. We have rotations and translations, but those are isometries of the background. Of our background, spatial translations and rotations are isometries, and so they're not going to do anything. We know how they act on correlation functions. Correlation functions will be strictly invariant under those two symmetries, so that's not what we're interested in. We're going to be interested in the dilation and the special conformal transformation part. Okay, so let's write them down. So we have for dilation, this guy is just a rescaling by lambda, and the special conformal transformation is the following thing. So this is the infinitesimal diff, just 2b dot x xi minus x squared bi. And we can trivially now compute how zeta transforms under these two transformations. And this will make contact with our discussion yesterday. So we find that, so by plugging in these diffs into the variation of zeta, you find that zeta under dilation, it's 1 plus x dot grad zeta. And under an SET, it's given by 2b dot x plus 2b dot x xi minus x squared bi zeta. Okay. So now let's compare this with what we discussed yesterday. So yesterday we wrote that a transformation of a field, let's consider dilation. In that case, we were thinking of this as a spectator field. We wrote that under this conformal group, we had the following transformation. It was delta plus x dot grad phi. Okay. So now I ask you to compare this expression with the one for zeta. And tell me the obvious differences. It's obvious, but I want you to say it, not me. Huh? Delta, so what is delta for zeta? 0. So indeed, there is no term which is just zeta here. It's just x dot grad. So as a result, from this immediately, and this will be important for later, the weight of zeta is 0. Okay? Which makes sense. It has mass dimension 0. It's a massless field. So perfect. It has weight dimension 0. And what else do you notice? You notice the constant bit. Okay? So you see that here there's a constant, not multiplied by zeta, whereas here it was completely multiplied by phi. So by definition, this is known as a nonlinear transformation. It's nonlinear because the answer is not proportional to phi. It's just a constant shift. So you see that zeta transforms nonlinearly both under dilation and under SET. By the way, this jargon of particle physics is rather confusing if you're not used to it. It's still it looks like a linear transformation, okay? But it's nonlinear in the sense that if you could think about the number of particles in each state, so here you start out with 0 particles and now you have some particles because you've given a vev to zeta. Okay, so that's nonlinear. And a nonlinear transformation of this type is the hallmark of a spontaneously broken symmetry. So this tells us that dilation and special conformal transformations are spontaneously broken. And in fact, since zeta is the quantity that transforms nonlinearly under those transformations, we identify zeta as the Goldstone boson for that spontaneous breaking. So this is very nice. So D and K are spontaneously broken And zeta is the gold stone. We identify zeta as the gold stone or the dilaton for the spontaneous, for the symmetry breaking pattern, which is SO4, 1, the group of conformal transformations on R3 being spontaneously broken, down to spatial translation and spatial rotations, which remain linearly realized, and that's the inhomogeneous special orthogonal group in 3 dimensions. Okay, so this is very nice. Yes. Very good. Yeah, that's a good question. I was not going to discuss this, but indeed, so the time dependence is completely arbitrary. Now, at the end of the day, this is not going to make any difference for the consistency relations I'm going to derive. But technically, we would like these diffs, as you know well, we would like these diffs to be the limit of a physical mode. And so you have to run through this adiabatic argument, which you can. And Paolo and friends did it for SET. And you find, so dilation by itself, demanding that it's an adiabatic mode, forces lambda to be time independent. For SET, it forces you to combine, B must be time independent, and moreover, you must combine it with a time dependent translation. And so that's true in general. There's always, but at the end of the day, the bottom line is there's always going to be a one-to-one map between the symmetries we identify and the number of ward identities. It's just you have to take certain linear combinations. By the way, at first sight, it's a bit surprising. So we're breaking here 4 symmetries, spontaneously breaking 4 symmetries, dilation and 3 special conformal transformations, and yet we only have 1 goldstone. Now, this is not a violation of Goldstone's theorem because we're breaking space-time symmetries. It's a well-known thing that with space-time symmetry breaking, you generically have fewer goldstones than broken symmetries. And you see already what's going on. So there's 1 goldstone, but of course there will still be 4 consistency relations that will ensue. And you can see it. You can see the physics here. Although there's 1 goldstone, you see that by the symmetry transformation, you're probing different moments of the goldstone. Here, just a constant, and here, a linear gradient. Before we go on, we can be more general and identify the most general diff. So we can solve this equation. So noting that, so if I want to solve star, noting that we don't get anything for free, we don't get anything new if things fall off at infinity. We just want things that grow. So let's just do a Taylor series around x equals 0 to find the most general solution. So more generally, let Ci be an infinite series, n equals 0 to infinity of 1 over n plus 1 factorial mi L0 Ln xL0 xLn. Okay, so a general polynomial. And you can see if you plug that in to this equation and solve order by order in x, it's clear that all you're demanding is some condition on the coefficient, and it's just a trace condition. So when you work it out, this array of m, which by the way, of course, is already symmetric by construction in its last n plus 1 indices by virtue of the fact that it's multiplied by a bunch of x's. But then if you, by star, you find an extra condition, which is that, so it's just a trace, mi LL, L2, Ln is minus a third, MLL, I, L2, Ln. Okay, so there's some trace condition on this array, which is, if you want, is the condition in order for you to stay in this gauge. Okay, so there's infinitely many symmetries that preserve this gauge. Okay, and they're all of arbitrary order in x. And there's a lot of, physically, it actually makes a lot of sense. You can do the counting. And before Merdad asked me a question about this, because we had some exchange about it, I'm going to be, for the purpose of the lecture, I'm going to brush over a subtlety having to do with tensor modes and adiabatic modes with the tensors. Please allow me to do that. But if you do the actual proper counting and you exchange a few emails with Merdad, you find the following answer. The physical picture at the end of the day is very beautiful. So imagine that you're a local observer in the universe. So here's your little region of space. And there is a long wavelength perturbation superseding you, okay, which is a combination of zeta and gamma. So locally, in your little environment, you can write the spatial metric, Hij. You can start writing it as a Taylor series. So Hij, I'll write it as bar to be the value at the origin of your patch, plus dk Hij xk, plus a half dk dl Hij xk xl, plus dot dot dot. So this is bar again. You do this Taylor series, and now you know, of course, that you can do coordinate transformation to simplify this metric. In particular, you can use coordinate freedom to set the constant mode to 0. You can make this delta Ij. There's enough freedom to do that. And that corresponds precisely, that freedom corresponds precisely with the number of these nonlinearly realized symmetries for dilation. So in particular, if there's a constant conformal mode, you can bring that to 0 simply by shifting zeta suitably. Similarly, you can also set the value of gamma locally to 0. You can also set the linear gradient to 0. That's just the equivalence principle. You can set this guy to 0, which corresponds to removing a constant acceleration. That's what this SET is doing by removing the linear gradient and zeta. And similarly, you can do that for gamma as well. So the first two terms you can make trivial. Now, as you know, at quadratic order, you cannot set that to 0. That's physical. Part of it is physical. It gives you, at best, if you want, you can go to Riemann normal coordinates. This will give you 1/3 Ricci, whatever, I, K, J, L, X, K, X, L. But if you count how many components, this is the Riemann tensor in 3 dimensions, how many components it has 6. And if you compare that to the number of components at quadratic order, there are more components at quadratic order. There are 12 if you do the counting right. And the difference between the number of components, which is 12, minus 6, is 6. And that's precisely the number of symmetries you have at quadratic order. You see? So the number of symmetries we have at each order is precisely the difference between arbitrary components in the Taylor expansion and the physical components, which you can write as in terms of Riemann and derivatives of Riemann at higher order. Okay? So it makes beautiful sense. At lowest order, it's just equivalence principle, and at higher order, it's just a redundancy of these different coefficients. Okay, so now that we've identified the symmetries, we can write down consistency relations associated with them. Questions so far just about the symmetries? Or? Okay. Let me take a bit of caffeine. By the way, I told this to Alberto, and caffeine powder is very dangerous. It's being sold on Amazon. There's an article in the New York Times. If you buy caffeine powder, they sell you 100 grams of it in a package. It's not regulated. You can buy it. But it's like almost as lethal as heroin. If you take a teaspoon of it, you die, okay? You have to take at the milligram level to measure it. It's like heroin, okay? So I'm just mentioning this. It's amazing. In the US, we're worried about many things, but somehow caffeine powder is totally fine. Okay. Yeah, somehow a teaspoon is like 25 cups of coffee, something like that. And the package is like 4,000 Starbucks coffee mugs. Okay. Ward identities. So here, let me give some credit. First to us. Sorry, it wasn't meant that way, but it just happened weird. Okay, so our paper. That's the one I gave earlier. And then there are many related papers of people in the audience, in particular Kohlberger, Hui, and Alberto. (1193). There's a paper by Bauman and Green. And then there's a paper by Paolo. And Marco. And it's very nice because these papers, they all get the same result using very different methods. So they're all complementary and worth reading. I'm going to focus on the method we followed for the only reason that it's a bit cumbersome, but at the end of the day, it's easily applicable to many different relations. Okay, so that's what I like about it, so I'm going to focus on that method. So let us start. Our starting point to write constraints on our correlation functions is a triviality. It's just the statement that the charge which generates these symmetry transformations, the charge commuted with the field, so let's just call it some arbitrary operator O, which will be a product of zetas and gammas. At the end of the day, by definition of Q being the charge, this is just given by the symmetry variation of this operator. Okay, it's a triviality, a tautology. That's what the charge does. And we're just going to take that statement and take its expectation value relative to the in vacuum. So to compute an in correlation function like we do in cosmology. Okay, so this is our starting point. And again, it's a tautology. And indeed, when we worked on this, we were getting 1 = 1 for a year. Okay? At some point, after a year, you managed to massage this to something non-trivial. But literally for a year, we were wondering whether we were just doing 1 = 1. But at the end of the day, you get a non-trivial statement. Okay, so first of all, if it, just to state an obvious point, if the symmetry were unbroken, we were talking about linearly realized symmetries, if the symmetry is linearly realized, then the statement is obvious. By definition, if the symmetry is unbroken, it's a symmetry of the vacuum. And so the charge acting on the vacuum would vanish by definition of the symmetry being unbroken. And as a result, the left-hand side would vanish identically. And so therefore, the statement that if a symmetry is linearly realized, it just tells you that your correlation function is invariant under the symmetry. Okay? That's like what we did yesterday under it. So 4,1, our correlators were invariant under that symmetry. If, on the other hand, the symmetry is nonlinearly realized, which is what we're considering today, if it's nonlinearly realized, in fact, what you get in that case, as we'll see, is a soft pion theorem. Analogous to what you find in QCD. Okay? So this is what we want to do. We want to compute a soft pion theorem for our symmetries. And it will suffice to simply focus on dilation, just to illustrate the method. And then once you've done it, the method can be applied to anything. In fact, it's easy to do it for all these x to the n transformations. So let's do it. So first, let's consider, right, so we're going to do the dilation as an example. And so for dilation, we have the following. We have that the symmetry transformation of zeta is 1 plus x dot grad zeta. The right-hand side is easy. So the right-hand, moreover, we're going to focus on, for simplicity, we're going to take O, this product of n fields, just for simplicity to make our life easier a little bit. I'm going to imagine this is a product of zetas, an equal time product of zetas. Okay? All right, here we go. So the right-hand side is easy because we did it yesterday. So the right-hand side, that was your homework, although I don't see any copies on my desk. The homework was simply to compute that the variation of O, actually we did this one, but the K1 was supposed to be U. Delta D of this guy is equal to exactly what we computed yesterday, but now we use the fact that zeta has vanishing weight, okay? So the answer for this, you just set all the deltas to 0, and what we found yesterday, so we had 3n minus 1 plus sum from a equals 1 to n of ka dot ddka acting on the correlation function. And remember, this factor of minus 1 was because we were stripping off the momentum conserving delta function, and so this is the answer. Okay, so that's the right-hand side. We're done. And now we want to extract something non-trivial about the left-hand side. So for the left-hand side, we have the charge. And so the charge, by definition, is such that if I commute it with zeta, I get the field transformation of zeta, which, as we said, is just a constant plus x dot grad. And, okay, so let me say the following. So you see that there are two parts of the transformation. One is the nonlinear shift, and the other one is the linear transformation. I'm going to split the charge accordingly. So let's split the charge as follows. Let's write Q as Q naught, the free part, plus an interacting part. Okay? And let me say why. And I claim that the free part, Q naught, generates the constant shift. So with Q naught commuted with zeta, it's equal to minus I. Okay? And the reason I call this guy the free part and this the interacting part is, let's think about it. Imagine you take your action and you expand it out in powers of zeta. You have the kinetic term for zeta, and then you have a bunch of interactions, cubic, quartic, etc., schematically of this form. By definition, the lowest order piece of the charge will be a symmetry of the lowest order piece of the action. Okay? And indeed, this is shift invariant under the shift symmetry. But now if I ask, is it invariant under this part, it's not. Because what will happen is that the linear shift of this piece, if I transform under this guy, I will get a term here which will be quadratic, right? And this will cancel against the lowest order transformation on the cubic term, which will give me something quadratic as well, you see? So as a result, this symmetry, this transformation can only be a symmetry of interactions, of a theory that includes interactions, whereas the lowest order piece is by itself a symmetry of the free theory. Does that make sense? Yes? Okay, so this is we're going to call this the free charge. It's the symmetry of the non-interacting theory. Okay, so what is a charge? Well, the charge must be such that when I commute it with zeta, I get a constant. So clearly, it's just the conjugate momentum to zeta. So indeed, we can write down Q naught explicitly. Q naught is just the integral d3x of the conjugate momentum of zeta, because clearly if I commute this conjugate momentum with zeta, I get a delta function, do the integral, I get 1. Okay? So that's what you need. And equivalently, I can think of this as the limit. If I were to put an e to the I q dot x here, I can think of this guy as the limit as q goes to 0 of the Fourier transform of the conjugate momentum. So this is equivalently the limit as q goes to 0 of pi zeta of q. It's the zero momentum limit of the conjugate momentum. Now I want to use basic concepts from scattering theory. So if you remember in quantum mechanics, when you do scattering theory, you usually do it off a central potential. And you define asymptotic states as follows. You define asymptotic states which, far away from the interaction potential, asymptote to free trajectories. Okay? So if this is the trajectory, this will be your in state, psi in, psi out. And you define these in states basically by taking the state of the system, evaluating to the far past using the full time evolution operator, and bringing it back home with the free time evolution operator. That's how you define these in states. And similarly for the out guys. Except for us, we're doing in, so really our picture is the other way around. So we want to think of it as some initial surface, Ti, and we want to define our in state to come in, to do some scattering, and bring it back. But the story is the same. We want to think of that near time, the initial time. Here, you'll have almost free evolution, both here and here. And then the definition of our omega states, our interacting vacuum, will be exactly the same as what you do in scattering theory. Okay, so in other words, our interacting vacuum, so omega, the in vacuum, well, let me just write it. So this in vacuum is related to the vacuum of the free theory, which we will choose to be the Bunch-Davies vacuum. If you want, that's the definition of Bunch-Davies vacuum. As usual, via a Euler operator. Okay, so this is Euler operator. It's defined, so first of all, this guy is the Bunch-Davies vacuum by definition. And this omega is by definition is this Euler operator. Okay, so this is the Euler operator. Okay, so the intuition is obvious. What you're doing is you take your state, okay, at time t equals 0. That's omega. You bring it back to the infinite past via the full time evolution operator, and you take it back home with the free time evolution operator, and that defines for you the interacting vacuum state. Okay. Just like in scattering theory. Perfect. Similarly, we can define, we will demand that our operators, in particular the charge, I should have said that as well. So when we do scattering theory, we demand that the potential is localized, or in other words, that far away from it, you have a free theory. Similarly here, we're going to demand that at initial times, our interactions turn off adiabatically. Okay, that's what we do in the in. So in the far past, these will be free interactions. So if I bring any operator, so I'm thinking Heisenberg picture, if I bring any operator in the Heisenberg picture back to the past, I should get the free theory operator. So that's true in particular of Q. So we have what's known as an intertwining relation for Q, namely that omega, the Euler operator Q, so that's just taking Q and bringing it to the past, okay? This guy will be just a free charge. Does that make sense? Yes? No? Yes? No? Okay, so let's disentangle this statement just to be clear. Right, what this statement implies is the following. If you want, if I were to unpackage it in terms of U and U naught, it tells the following statement. It says that U dagger minus infinity 0 Q, U minus infinity 0 is equal to U naught dagger Q0 U naught minus infinity 0. It tells me that Q, you bring it backwards in time to minus infinity. It agrees to the operator Q naught brought back to minus infinity according to the free time evolution operator. Okay? It's exactly the same statement as saying I'm turning off interactions in the far past. Okay? If you open Weinberg's book in the chapter on S matrix, he exactly assumes this for in and out states, but now where he takes the Hamiltonian or the momenta or all kinds of operators obeying these kinds of relations. Okay. So that's your homework tonight. You open Weinberg page whatsoever. You read S matrix story. It's exactly that. Okay, so now with these simple statements, we can get a long way. So we have the following. So in particular, this intertwining relation, if you want, this intertwining relation implies the following. Equivalently, Q times omega minus is equal to omega, the Moilo operator, times Q naught. So in other words, when I commute this Moiler operator, I transform the operator into its free partner. And so that's it. Now we can apply this to our identity. On the left-hand side of our identity, we had the charge acting on the vacuum. We had Q acting on omega. And so here we go. Q acting on omega is Q times, by definition of the in vacuum, times the molar operator acting on the Bunch-Davies. And then I can commute the molar operator past the charge, metamorphosing it into the free charge in the process. So this simply becomes omega minus infinity, Q naught acting on the free vacuum. Okay? So it's deceivingly simple, but it's amazing because now we've turned the problem, this rather complicated problem of acting with the full charge on the fully interacting vacuum, we've translated it to a problem of acting with a free charge on the free theory vacuum. And that we can all do. Okay? So we just have to do that, and then we're done. So let's do it. We just have to compute the free charge, which is here. Let's leave it. The free charge acting on the Bunch-Davies vacuum. Yes? Ah, very nice. It's the same. It's the same. So if you want, this usual I epsilon deforming the contour business is equivalent to turning off interactions in the far past, because it basically, it takes, it maps e to the minus I kt. It adds to it a damping part, like so. Okay? So it's precisely, the I epsilon trick is exactly a way, it's exactly equivalent to this. Exactly equivalent in a way that nobody has made precise, but anyways. It is exactly a way of shutting things off in the past, okay? But it's true, nobody has quite, in the literature, made this very precise. But indeed, it's exactly correct. So it's just, that's by definition, it's by definition the Bunch-Davies vacuum when you do that. Absolutely. Okay. Yeah, I should say this is, yeah, if you get me going on this, I can keep going. Because the point is that in non-equilibrium theory, people have considered problems like this. But usually they consider problems where you have a Hamiltonian which splits into a free Hamiltonian, which is time independent, plus an interaction piece, which is time dependent. That's the type of problem people are interested in non-equilibrium dynamics. But then by hand, they can then turn this guy off with an exponential, okay, adiabatically, which is what, as you said. The complication in cosmology is that even the free part is itself time dependent, okay? So anyways, I couldn't find any precise analog in the literature in non-equilibrium dynamics, but at the end of the day, yeah. Okay. So let us now compute this free charge acting on the free vacuum. And this is quite remarkable. It sounds very simple, but this is again where we kept getting 1 equals 1. It's very nice, actually, because the simplest way to do this, I think, is to actually use the Schrödinger picture of field theory, which people rarely use, but for this purpose, it's actually exactly what the doctor orders. So we're going to actually think in terms of the Schrödinger picture. So in the Schrödinger picture, okay, as you know, our operators are time independent. So in particular, so in other words, I'm thinking in Schrödinger picture. In the Schrödinger picture, we have that our field operators zeta is actually time independent. So it's a pure function of x. And the eigenstates of this guy are also time independent. They're just basis states. And so actually we're going to consider eigenstates of the free zeta operator. Actually, in Schrodinger picture, I think it doesn't matter whether they're free, the operators are free or not. Doesn't matter. So we're going to define this guy as the eigenstate under zeta. Like so. Okay, we're on the left-hand side as an operator, on the right-hand side as a function. And we're going to insert a complete set of states of these guys. It's exactly what you do in quantum mechanics. So we want to compute this charge. So Q naught acting on the vacuum is equal to, so it's equal to this pi. It's the momentum acting on the free vacuum. So we have limit as Q goes to 0 of pi, the conjugate momentum acting on the free theory vacuum. And this is exactly like in quantum mechanics. You want to find how P, the momentum operator, acts on a particular state. And it's often convenient to go in the real space representation in which P is just ddx. Yes, so that's exactly what we do. We insert a complete set of states. So it's a continuous basis. So we have integral over xi naught. Let me erase the charge at the bottom. We have the integral, so complete set of states. So xi naught, pi. Sorry, I had my limit. Let's put it outside. Limit as Q goes to 0. Pi zeta of Q of naught. Okay? So this is indeed the real space or configuration space representation of how P acts on a state. So it's just given by ddx on the wave function, in this case dd zeta. And by the way, this is not a path integral. It's a good old ordinary integral, just over all possible configurations of zeta. So now the limit, Q goes to 0, integral d zeta, zeta naught, minus I, function of the derivative with respect to zeta of minus Q. If you work it out, it's minus Q instead of Q, acting on the wave functional, the real space wave function, the real space, the configuration space representation of the Bunch-Davies vacuum. Does it make sense? It's just quantum mechanics on steroids, okay? Yeah. Yeah. Sorry, what? U. Q. Yes. It's just an operator on the Hilbert space. It's a charge operator, and it generates the transformation when commuted with zeta. Yeah. Yeah, in fact, it's not it's like saying the analog, there's the precise analog in quantum mechanics is, so here we're shifting zeta by a constant. That's like the analog of shifting the position operator by a constant. And you know that in quantum mechanics, the generator of translation is just P, since P commuted with X is I. And similarly here, the generator, so this would be the charge. Here the charge is the conjugate momentum zeta, and et cetera. The analogy is perfect. Except that zeta is not just a, yeah, it's a field. But otherwise, the techniques are the same. So to compute this quantity, we just need to have the wave functional representation of the Bunch-Davies vacuum. And that's easy, because the Bunch-Davies vacuum is just a Gaussian. So now we plug in the Bunch-Davies vacuum. It's just a Gaussian, so we can represent it easily. It's a Gaussian because it's the ground state of a harmonic oscillator, and we know the harmonic oscillator has ground state, which is a Gaussian, so no surprise here. It's just a Gaussian as well. So it's an exponential, except that I have a sum over all possible oscillators. So I integrate over d3k, zeta k, and the variance of this guy is the power spectrum, or 1 over the power spectrum. which you can check if you compute the two-point function using this wave functional. I tell you, it's just like quantum mechanics. So just compute the two-point expectation value. The variance should match the power spectrum, and you'll find it's exactly 1 over p that you need here to match the correct answer. Sorry, can you, the S, 1, sigma 3? So. No, so no. So yeah, no. That's right. So what I'm aiming at here is just to find how. That's right. I'm just getting to the point where I can show how this charge acts on the vacuum at the end of the day. So that's just the point of this exercise. Okay. No, it's not 0. That's the point. That's right. Okay. Very good. So we're done. So we can compute now this functional derivative. On this state, since it's just a Gaussian, you can see what happens. I'm just going to bring down a power of 1 over p times zeta. And when you put all the right factors, yeah, so dot, 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 that's easy. And so here's the answer, that the charge Q naught acting on naught. All right, so you do that, you undo the completeness relation, and here's what you find. This is for tonight in the privacy of your room. You find the limit, Q naught goes to 0, 1 over 2 p zeta of Q times the free field zeta naught Q acting on the Bunch-Davies vacuum. And now it's an operator statement, and so I can think of it in any picture I want. So let's think again back now in terms of the Heisenberg. Let's think back in terms of the Heisenberg picture. We revert back to the Heisenberg picture now. So if you want, what I mean by zeta naught here, so I should say this guy now depends on time in the Heisenberg picture. And what I mean by zeta naught is the field which evolves in time according to the free Hamiltonian. Okay. Very nice. So we're done. Except for one technical assumption. And by the way, let me make a comment that what's very nice about this derivation, although it looks a little bit technical, is that it's very clear where the initial state comes in. The initial state came in right here. So you want to modify Bunch-Davies, because you feel like it, you could just add extra terms. You could add a zeta cube term, and so on and so forth. This will directly descend into your variation, and so on and so forth. So the assumption about the initial state is manifest in this way of doing it. Now, the final assumption, which is really a necessary condition for this consistency relation, is the fact that zeta must go to a constant at long wavelengths. So this is where the assumption comes in. So if the growing mode for zeta is a constant, so in other words, if the limit as q goes to 0 of zeta of q is a constant, okay, so if the growing mode is a constant, and similarly for the free guy, so limit as q goes to 0 of the free operator, so in the long wavelength limit it tends to a constant, then since these guys in that limit are just constant operator, clearly they don't care how I time evolve them, and so in particular this implies that they obey, just like the charge, they obey an intertwining relation. So namely, the limit as q goes to 0 of omega. So if I bring this guy past if I bring a modular operator past zeta, I turn it into the free zeta. So this is where the assumption of constancy of zeta comes in. Okay, so let's recap where we were, and essentially we're done. In fact, it's right here. So we started out on the left-hand side with Q acting on the in vacuum. We turned this into the free charge acting on the free vacuum. Okay? So now let's write the result. The result is we have the Euler operator acting on this object over here, Q naught on the free vacuum. So let's write this out. We have limit as Q goes to 0, 1 over 2p zeta Q, zeta of Q, and this whole thing acting on the free vacuum. Sorry, this was the free field. And then we can undo, bring back the Euler operator through, use the fact that zeta is conserved, as we just showed. When I bring it through, it turns zeta naught into honest to goodness zeta. And then omega will act on naught and make it the interacting theory vacuum. So that's the last step. This quantity is equal to simply the limit as Q goes to 0, 1 over 2p zeta of Q times the full zeta acting on the full vacuum of the theory. And so that's it. The only thing we haven't done is to take a commutator, but that's easy. So I was a little bit delinquent. There was an imaginary part here which I dropped. The imaginary part cancels. Yes, Medad. Oh, sorry, yeah, absolutely. Thank you. Yes, I was zooming out. Yes, absolutely. So here also there should be a limit as well. Thanks. So this should be zeta naught and then omega. Yes. Yes. And then the last disclaimer is that here there should have been also a phase bit, okay, from the wave functional. But this cancels out. It would carry on all the way here. There would be an extra correction. But remember, at the end of the day, we're taking the commutator, Q with O, and then in that case, that imaginary part drops out. Okay? So at the end of the day, you get the following statement. At the end of the day, we have, and we're done, we have the statement that the left-hand side, which was this inner product, this expectation value of Q commuted with an arbitrary product of zetas. This guy, therefore, we've shown, is the limit as Q goes to 0. Oh, and by the way, when you take the commutator, also the factor of a half becomes 1. So it just becomes 1 over P, zeta of Q, omega, zeta of Q, O. O, which depends K1, Kn. Very nice. And then the right-hand side, we know what it is. This guy is equal to the variation of O, and so that's it. So it's this variation of O, which we wrote down earlier. It was minus this 3n minus 1 minus Ka sum Ka dot ddka on O. Yeah? Prime. Yes, prime, and that's it. So as advocated, in this case, because it's a nonlinearly realized symmetry, what we have is not that the correlator is invariant, but instead the variation of the correlator is related to inserting a soft mode of the Goldstone. Okay, this is exactly what happens. It's exactly what happens, for example, with the soft pion theorems. Having a soft pion, soft momentum pion, gets related to a symmetry transformation of the correlation function without the soft mode. Let's see if the computer works. That's probably the trickiest part. Let's see. Laptop. I don't know. Oh, it's there. It's there. Maybe it's just warming up.
It's coming.
Yes.
Okay.
Okay.
Don't want to spoil the joke. So.
No, there's no joke this time. Okay, so I'll just show you some results that come out of this. So this is our conclusion of what we did on the board. You can generalize this now to all the other transformations we found. So in particular, we found that at high order, we had delta zeta and delta gamma. Remember, we found an infinite number of these transformations that went as x to the n. If the transformation goes as x to the n, on the left-hand side, this will correspond to many derivatives, the same number of derivatives acting on the soft mode. Okay, so for arbitrary n, this is what you see. This is the structure of the consistency relations. So it's n derivatives with respect to q of these correlation functions. And now in general, they involve a soft zeta mode and a soft tensor mode. And they get related to the corresponding symmetry variation of the operator O. And again, based on our thinking of the equivalence principle, the leading order, so Q naught and Q, which was the constant part and the linear gradient part, they're completely fixed. Okay, so if you think of this guy as a Taylor series in Q, the constant bit and the leading order and the first order in Q, they're completely fixed in terms of the lower point function. But at higher order, it's only partially fixed. Okay, just partial information about the Taylor coefficients. These are physical statements, okay, in the sense that there was a physical assumption that went into them, and then the physical assumption was that zeta was constant outside the horizon. Okay, so these guys can be violated. In fact, you can test, for example, when we try to measure FNL, we're precisely trying to check the validity of these consistency relations. And one thing I want to stress, which a priori is a little bit surprising, but notice that we didn't assume anything about inflation. We didn't assume slow roll. This is exact statement arbitrarily far from slow roll. So this is kind of remarkable because it basically says, so somehow our symmetry breaking pattern, remember our symmetry breaking pattern was SO4, 1 broken to ISO 3. And this guy, it's linearly realized exactly at the de Sitter point. And you might expect that only for small departures from de Sitter you have the symmetry, but in fact, arbitrarily large departures, the symmetry breaking pattern. So it's like de Sitter is the point where the symmetry gets restored. It's the exact point where symmetry is restored, and the deviation from it is described by this symmetry breaking pattern. Oh, sorry, the clicker doesn't work. I'm moving arbitrarily far, but for no good reason. Let's continue. This is how they look. This was the schematic form. This is actually how they look. Okay, so when you put all the indices and stuff. And of course, okay, so as particular cases, you reproduce things that people knew, that Paolo and Matthias in particular had derived using other methods. But then you get other new statements. So in particular, at n equals 2, corresponding to a quadratic shift in the coordinate, you get a new statement. So here's one. I check this at some point, and it works. Okay, so left-hand side matches right-hand side. It's very nice. And that's as much as I could do. So then I hire young people who can do a much better job than me. So these guys, Berizjani and Wang, they did some amazing stuff. So you can do, so I'll show you. Actually, let's not go too fast. Okay, so here's the schematic form of the consistency relation. And the right-hand side, so this is for arbitrary sound speed. The power spectrum of zeta goes as 1 over epsilon times CS. Okay, so let's just check the parametric dependence just for this discussion. On the left-hand side, you find that at up to order q squared, this is the dependence. Okay, so zeta starts at order q squared, in this case, a 3-point function. And gamma has beautifully the right parametric dependence. You do the check, it works out, as you'd expect. But then at order q squared, there's a paradox. It's not much of a paradox, but it's a bit non-trivial. So you see that at order q squared, you see that the answer for zeta goes as 1 over cs cubed. And the answer for gamma also goes as 1 over cs cubed. All right? So for the identity to work out, these two contributions, the 1 over cs cubed must cancel, leaving you with the 1 over cs. And indeed, that's exactly what happens. Okay? So somehow the two of them, they conspire to give you the right answer. And so Lasha and Jumpu, they did all these checks. So all the 3 to 2 checks up to q to the 3. Okay? And so that's very nice. So it works. Okay? Then you can do, also another thing you can do is to do multiple soft limits. And this was work with my former student, Austin Joyce and Marco. And so the intuition comes from pions that if you take multiple soft limits, that's another way to probe higher Q dependence. Basically because for each leg, you're differentiating with respect to Q. So for example, if you take so here's our general result at the end of the day. So if I take 2 soft limits, okay, 2 soft limits with respect to Q1 and Q2, now I'm going to get, you're basically getting things at order Q squared. So 2 derivatives with respect to Q, in other words. Okay, so, and you basically get, it's basically this structure where either 2 legs are acting on the hard legs, or you get an exchange diagram of this type. And you can also derive this alternatively, and this was what Alberto and collaborators followed. You can work this out, instead of thinking in terms of operator formalism, you can work it out in a path integral fashion as a Slavnov-Taylor identity. So here's something that you've seen in your quantum field theory course. If you, in E&M, so after all these symmetries are diffeomorphisms, so they're really originating from a gauge symmetry. And you know that in E&M, gauge symmetry relates vertices. So in particular, the 3-point vertex involving a photon and fermions is related to the fermion propagator when you contract with the 4 momentum of the photon. Okay, so this follows directly from the gauge invariance of the theory. It's known as the Ward-Takahashi identity. And so you can do the same thing in gravity. Okay, so here's the answer you get at the end of the day. You get something about the vertex functional varied with respect to zeta and with gamma being related to something on the right-hand side. And then you can take this sort of master identity and vary it a bunch of times with respect to zeta or gamma to get the corresponding identities. So here it is. So in other words, this is at the level of vertices as opposed to being correlation functions. So here it is for the 3-point function. So you see something very similar to what we've derived. You have the 3-point vertex for zeta and 3-point vertex involving a tensor. It's related to the 2-point function of zeta. Okay? And this statement is exact in Q. There's no expansion. But at the end of the day, to turn it into a statement about correlation functions, you have to do the translations. You turn vertices into correlators. Sorry, I'm going fast, but this is just to give you a flavor. In fact, I ran out of slides. That was not supposed to happen. But anyways, sorry, it's here. Yeah, so you do, yes, sorry. I thought I didn't have the punchline. Thankfully, I do. Yes, so you convert to lines, going from vertices to lines, and this is the final statement, which is exactly what we got. Okay. So that's all I had to say. And in this Slavnov-Taylor way of doing things, what is nice is that the assumptions about zeta being constant, you can make it even more precise. Let me just say a quick word about that. So when you turn this identity for vertices in terms, when you try to solve it for the vertices, you find there's an ambiguous part, Aij, which is a physical part. This is the part actually which corresponds to the physical violation of the identity. And at the end of the day, the assumption that zeta is constant outside the horizon amounts to an analyticity property of this guy. And so as long as it starts at q squared, you can keep going and you get the result we derived. Okay, I know this was fast. This was just to give you a flavor of these consistency relations. But what we did today for dilation, it's very easy to do it for these arbitrary transformations. Okay, thank you.